So we'll get into the new topic, system of linear equations. System of linear equations. Linear equation, so the equations are going to be of first order. Obviously linear in the sense means we cannot have a function which is non-linear, like we can write ax plus by equal to c. Then with a and b being a scalar, c being a scalar, we'll see that this is a first order equation, right? But instead of c, if we write sine x, this becomes nonlinear. If instead of x we write x squared, this becomes nonlinear, right? So we have to make sure that it is a first order and all the elements are, or the functions of x or y are linear elements, not nonlinear, right? So a system, let's say, of m equations in n unknowns. Let's say we have equation, so unknowns, n unknowns in the sense, we say x, the unknowns are x1, x2 and so on, xn. The equation may be of the form a11 x1 plus a12 x2 a1 n xn equal to some constant b1, right? a21 x1 plus a22 x2 so on b2, and likewise we'll have m such equations, so it will be m1 x1 mn as the last element equal to bn. It will be bn. So this is the system of linear equations. We have m equations with n unknowns, right? So overall this equation can again be written as, it can be written as again as ax is equal to b, or you can write it maybe in the sense of capital B, where a is the coefficient matrix, that is a11 a12 so on a1n, and likewise up to m1 m2 mn. So this becomes your coefficient matrix, and this x is the unknown vector, which can be written as x1 x2 up to xn, being n number of, this b is the constant on the other side, b1 b2 and then bn likewise, right? So if this b becomes null, what will happen? The equation becomes ax equal to 0, and this is nothing but homogeneous equation. And if b is not null, or you can say if for b at least one element bi is not equal to 0, then this ax equal to b is non-homogeneous. So this is non-homogeneous equation, right? Now we'll see what is A augmented B. So now we know this AX is equal to B. This A is M cross N matrix, and this is, I'll say, number of rows was 1, M, so M into 1, right? Number of rows are same. So if you are writing A and B together, this is known as A augmented B. This becomes a matrix of size M cross N plus 1, right? There's one extra column for the column of B which comes together with A, right? So this is like A11, A21, AM1, A21, 22, 1N, and along with this, with a dotted line, we can represent this B column as B1, B2, and so on up to Bm. So this together, a matrix of size M cross N plus 1 is the A augmented B, where we'll be keeping this B along with the coefficient matrix, right? And we'll see that how it is actually making any sense. So for Ax is equal to B, let's understand this, like what is the solution and what is the solution of system of linear equation first. Like let's assume that the number of unknowns are 2, right? So we are writing an equation as A11x1 plus A12x2 equal to B1, and A21x1 plus A22x2 is equal to B2. So these are, you remember, Ax plus By equal to C. So x1 is x, x2 is y, x1 is x, x2 is y. So this is two straight line given, right? Geometrically these are two straight lines, and we'll have to see that what are the possibility of solutions and what it means in the geometrical sense. Possibly two lines can intersect somewhere, two lines may run parallel, and two lines may coincide, right? So for, let's say, this is line 1, this is line 2, which are the equations of a straight line like this and these two equations. So this is simultaneously satisfying, this point is simultaneously satisfying both the equation, and this is unique, or I'll say one solution. These two are parallel lines, they will never meet, so this is like no solution. And this is like coinciding lines, so they'll always have all the points satisfying both the equations, so it is infinite or many solutions, right? So these two cases are the cases of this one, and this one are the cases of consistent solution, which means the solution exists, where this is inconsistent, that is solution does not exist, right? Now we'll see. So let's see how to find the solutions as per the Gauss elimination. Gauss elimination and back substitution, right? So we have seen the A augmented B matrix, which is A augmented B, also written as, or A cap. So what we can do is this A augmented B can be transformed into a triangular form by some elementary transformations, elementary operations, and then we can apply the back substitution to find the variables. Like we can start with xn, then xn n minus 1 and so on, and we can find all the values, right? So we have to make this A augmented B into elementary triangular form, and for this we can follow certain row elementary operations. That is, we can, instead of any row or column, both, we can write Ri plus k times of Rj. That is, we are adding a scalar multiple of another row to that Rith row, right? Similarly, we can also change any row and multiply with some scalar. So we can multiply a row. Obviously, like you have a straight line ax plus by equal to c, then you can multiply this equation with 2, and 2ax plus 2by plus 2c will still give you the same equation and will still coincide if it is coinciding with another line. And of course, you can change any rows or columns. Ri can be exchanged with Rj, because it doesn't matter. It doesn't matter if you are writing the first equation first and then second equation. If you have two equations, let's say equation 1 and equation 2, does it matter if you are writing the first equation first and as a row 1 and then the second equation as row 2? What if we exchange it? What if we are writing equation 1 as equation in the row 2 and equation 2 in the row 1? Will that not give the same solution? It will give the same solution, right? So these all operations can be done so that we can change the A augmented B into a triangular form. We can transform into a triangular form, and then starting from the last row, we can start finding the unknowns, and back substitution will help you to find all the unknowns, right? So any such operation will change the system of solution. But what if we are doing this elementary operations in the terms of columns? Can we do it in the terms of column, like column 1 is equal to column 1 plus 2 times of column 2? The answer is no. No such, I'll say, no such column operations are allowed, right? Because if we are applying column operations, elementary operation for the columns, it will change the sense of equation and it will change the entire equation, and the solutions will also be different, right? So let's see one example.